evening, guys. I hope you're doing well. Again, this is the material for Lecture 6. We're going to go ahead and get started with a review from Lecture 5, and then we'll move into the material for Lecture 6. I hope that this will be a fairly short lecture, and I hope that it won't be terribly confusing. So let's see how we can do with that, okay? All right. So starting with review. So with the review questions, I have 5 grams of water in 4.63 liters of ethanol. So what's the solvent here? Well, which one is bigger? 4.63 liters of ethanol. So ethanol is the solvent. The solute, the smaller amount that's dissolved in that, is the 5 grams of water. Now, is that an aqueous solution? Actually, the answer to that is no, because it's not something dissolved in water. It's water being dissolved in something else. So it's sort of a trick question, but it's not actually an aqueous solution. So you need to know that that's the case. Looking at HCl and CH3COOH, so hydrochloric acid and acetic acid, which one is a strong electrolyte? Well, which one completely dissolves? That's what we're talking about there. HCl is the one that completely dissolves. Remember that H comes off and we get H plus and Cl minus. Which CH3COOH, we lose this last proton, the one that's right here, but it doesn't completely react. Not all of it will react. And so it's a reversible reaction. That makes this a weak electrolyte. All right, CaNO32 plus NaOH. Excuse me. So what are your products here? Well, let's pull up our whiteboard. Let's see what we can do with that. Find my cute little pencil here. That's not a pencil, that's an eraser. CaNO3 2 plus. And that was NaOH, yes? Yes. Just checking. Okay. So we're going to have a reaction here. And this is what we call a double displacement reaction, also known as a metathesis. So the cation from here, the Ca2 plus, goes with the anion from here, the OH minus. And since it's 2 plus on the Ca and 1 minus on the OH, let's delete our charge there. We know we need to have CaOH2 to make that charge balance. So again, this is 2 plus, this one is 2 minus, or 1 minus, and so we need to multiply that by 2. What else do we have? Well, I have Na, the cation from here, which is a plus 1, going with NO3, which is a minus 1. So it's NaNO3. Really? And of course, in order to balance that, I have 2 NO3s here. I have 1 OH here. I know I'm going to have 2 OH groups. That means that I have 2 NAs, 2 NO3s. That's going to give me a 2 there. So that's balanced for that. Now, is that everything that we need to do to make this work? No, actually it's not. I need to talk about what state each of these is in. CaNO3 is an aqueous. NaOH is aqueous. My NaNO3 is aqueous. And I say that because salts of the alkali metals, those group 1 metals, are soluble. In addition, salts of NO3 minus are almost always soluble as well. When we talk about this other one over here, the CaOH, is that one soluble? And actually the answer there is no. So this one is a solid. Why is it a solid? Because it's an OH minus. Almost all of the OH minus compounds are going to be solids in solution. There are a few exceptions to that, and they're usually the alkali metals. So things that we talk about, NaOH, KOH, RbOH, LiOH. Those are soluble compounds, okay? So that's how we talk about it. Those are our products. Whew. All right, so those are our products. Are all your products soluble? No, they're not, which we just talked about. Write a net ionic equation for the formation of a solid product if one forms. Well, one did form. which one formed the CaOH2. Now, if we want to talk about the net ionic, we typically talk about writing the ionic first. And this is not going to fit. I can guarantee that. So Ca2 plus aqueous plus NO3 minus aqueous plus 2Na plus aqueous plus 2OH minus aqueous. Going to, and I'm just going to move this down here because I know it's not going to fit. CaOH 2 solid plus 2Na plus aqueous plus 2NO3 minus, again, this is aqueous. Now that's our complete ionic equation. But if we want to talk about the net ionic, we need to get rid of anything that's just standing around, those spectator ions, things that are not involved in the formation of the solid. So we want to get rid of the NO3, we want to get rid of the Na. So we get rid of the Na, we get rid of the NO3. That leaves us with Ca2 plus aqueous plus 2OH minus aqueous goes to CaOH2 solid. Now, can I do that without doing the whole ionic equation? Yes, I can. I've been doing this for a while. So I can see that the Ca2 plus goes with the OH minus, the two OH minuses, to make CaOH2, and I don't need to write the rest of it. But if they ask you for the ionic equation as well as the ionic, then you have to indicate both. If they can ask you to just go straight to the net ionic equation, there is no reason for you to write the full ionic equation unless it helps you. And if it does, feel free. Absolutely, go for it. Okay? So hopefully there are no questions about that. There are some little answers down in the notes to this in case you need them. But that's how we get that material, all right? So that's our review. Yahoo! Now let's talk about the material for lecture 6. First thing we talk about, molar concentration. What this amounts to is the amount of solute present in a given amount of solvent or solution. While concentration can have many units, the one we're going to start with is molarity. It's capitalized by a large M. So molarity, the large M, is equal to the moles of solute in liters of solution. So it's moles per liter equal to N over V. Now this is an intensive property. It's not dependent on how much of the solution is present. It doesn't matter how much of the solution I take, it all has the same properties. This is true only for the amount of solute originally given in that volume. So if I change that volume, then the molarity is going to change. So if the volume changes by addition of water, then the concentration changes. Okay? If I add more solid, it changes. If I change the volume of the liquid that it's in, then it changes. Please note the details of how to properly make a solution of known concentration given on page 150, chapter 4, section 5. Now that is typically a lab issue, but please make sure that you've read that, because one of the things that we need to make sure that we do when we make solutions in the lab is that they are accurate. And in order for us to do that, we have to make sure that we've made them appropriately. In the labs that we do here, we typically make those solutions for you, but if you're asked to make a dilution of a solution, you need to know how to properly do that. And then that information is found in your textbook, okay? So dilution of solutions. Oh, we talked about dilution just a minute ago. We said that the concentration was going to change, and it is. So when we add additional solvent, that usually in this case we're talking about water, then the concentration changes. In that case, and that case alone, you can calculate the new concentration by using the formula M1V1 equals M2V2. Initial molarity, initial volume is equal to final molarity, final volume. Okay? When we're doing this, we're typically looking for the new molarity because we know what solution we started with, so the concentration and the volume, and we know the final volume that we made. So we need to be able to calculate what's that new concentration. If we're doing that, we're looking for M2, so we can rearrange this to have M2 equal to M1 times V1 divided by V2 to calculate that value. Now, we don't need to do that in any particular units. As long as the volumes are in the same units, doesn't matter what they are, they will cancel out. And it doesn't really matter what units we're in for any of this. So it could be a molarity. It could be a molarity, could be a molality, really doesn't matter. We just need to know that whatever units they are, that's what they're going to be at the end, okay? So that calculation works because the number of moles of solute does not change, but the total volume has changed. Okay, so we haven't added or taken away any of the material that was present. We just added more volume to it, and so we can change that molarity through that process. Okay, now please understand that this is not how we do stoichiometry. So this is not how we do calculations to determine how much of a material is present. This is only applicable when we talk about diluting solutions. It's the only time it works, okay? Questions about any of that? I hope not. Gravimetric analysis. Oh, Lord. All right. Well, what is gravimetric analysis? I can mix two solutions to form a precipitate, an insoluble solid. We talked about how we determine if it's an insoluble solid before, which can then be separated from the solution. So I can find a way to pull off that solid precipitate. The mass of the solid, once it's dried out, can then be determined, and it will tell you how much of the material was present in the initial solution. Okay, all of that I'm sure makes absolutely no sense. If I take a solution of AgNO3 and I react it with NaCl, I get NaNO3 and AgCl solid. So if I have a solution of an unknown AgNO3, so I don't know what that concentration is, and a known concentration of NaCl, when the AgCl is isolated, it will tell you how much AgNO3 was present. Let's see how that works. 25.000 milliliters of unknown silver nitrate solution is reacted with 15.631 milliliters of a 0.250 molar NaCl. What is the initial concentration of the silver nitrate? 15.631 milliliters of NaCl, which is 0.250 moles per liter of NaCl. We can multiply those two together. So we take that volume. Let me get my annotation. Sorry. So if I take that volume that I started with, 15.631 milliliters of NaCl, I multiply that by the molarity, the 0.251 moles per liter. That will give me a number of moles of NaCl. Now, I need to have that converted because this is milliliters and this is liters. So I need to convert that by dividing this by 1,000 milliliters. That way both units cancel. I'm left with moles of NaCl. Now, I can cancel my moles of NaCl by dividing by 1 mole of NaCl is required to react with 1 mole of AgNO3, and that's from the stoichiometry of this equation, remember? So we have 1 mole of AgNO3, 1 mole of NaCl, and that's where this ratio comes from. We then divide this by the volume of the unknown solution. So 25.00 should be 3 zeros. And then multiply that by 1,000 milliliters again. Now you'll notice we multiply by 1,000 here. We divide by 1,000 here. So is it required that we do this? No, technically it's not. But when I do this, it only makes sense to me if I cancel all my units the way that I think that I need to. I don't like to do pre-calculations where I change this from milliliters to liters. I don't like to do that. I think it complicates things, so I always do it stepwise, just like you see here. Now, if I do all of that happy math, what do I find out? Well, I find out that 0.1563 moles of AgNO3 per liter. Okay, so it's a different molarity, but I know exactly what that molarity is based on the reaction that was done with a known solution. So since I know the molarity of the NaCl, I can find out the molarity of the AgNO3. That's exciting, isn't it? It is. I really think that it is because it can help us to identify unknown solutions tell us exactly how much of that material is present. We can use precipitations like this to identify solids. And so we precipitate them out, we figure out what they are, we figure out what their concentration was. All of these things can be done, and these things are typically called analytical chemistry, where we're analyzing to see what we have. This particular process is called gravimetric analysis, and that's where we form a solid, which we then isolate, find its mass to do the calculations that you see here to find out information about our starting solution. Okay? All right, let me turn off my annotations, and let's continue. Note that we only know the concentration of the Ag+ ion, not the entire species. If we had not been told that it was AgNO3, we'd have no idea. All we know from this slide here is that the Ag reacted with the Cl to give us AgCl solid. That's all we know. All right. So we were told it was AgNO3, but we don't have to be told that. We don't necessarily know that to begin with. Okay. We can combine this analysis with a percent by mass to help us determine the identity of the anion, since no two compounds containing the same ion have the same percent composition by mass. So we can use that. If we can identify the product that we've made, we can then do some combinations of those two analyses to see what we have. We are not going to do that in this class. I'm not going to force you to do that, but that is something that can be done. Only reactions that can be driven nearly to completion will work for this type of analysis. Otherwise, we have no way of knowing how many of the ions did not react. So how can we force that? Well, we'll talk about that a little bit later. There are ways that we can force this to go forward, even if it's not a reaction that normally goes to completion. But we can do that. We can force that, and we will talk about how we do that later. Right now, we're going to continue to talk about some of these reactions that we do to figure out what we're working with. All right. So questions, comments, problems, if you have them, make note of the lecture number, the approximate time, and your question. Send them to me via email, and I will do my best to answer them or bring them to an officer. Thanks. So titrations. Oh, I just talked about titrations, didn't I? Yes, I did. Now, precipitation reactions can be titrations. What we just described was actually a form of titration. Gravimetric analysis is a form of titration. We'll start with acid-base titrations to talk about them in more detail. We know that acids and bases can react to give us salt and water. We talked about that before. We can use that neutralization reaction to identify the concentration and identity of one of those two species, as long as the other material is a well-known composition. That means standardization. Okay, what the hell am I talking about? Well, let's see if we can make a little more sense of that. So if we're talking about NaOH, a solid reacts with water and CO2 in the air. So its composition is difficult to specify from the amount of solid that we've used to make that solution. So NaOH as a solid can pick up water from the air. If it's not completely dried, we can force that. But it can also react with CO2 from the air to form different things in the solid. So it's difficult to say exactly what its concentration is. But we can use a standard like KHP to determine the concentration of the base solution once it's made. Now, KHP is available in a highly pure form, so it's good for standardization. KHP is this structure right here, KHC8H4O4, has a molar mass of 204.2. It is monoprotic, so it reacts with just this one proton, reacts with the NaOH, so it's a one-to-one reaction. The net ionic equation for the reaction of KHP with NaOH is as follows. So we take that potassium off of it. We have the HP plus OH goes to H2O plus this C8H4O4 2-. All we really care about is this is a monoprotic reaction. It's a one-to-one relationship. So if I know what the concentration of the KHP is, then I can figure out what the concentration of the NaOH is. Okay, so that's what we're talking about for this. All right, awesome. In order to do this, we need to talk about something that's a little bit different. Now, what is an equivalence point? What is an endpoint? Well, an equivalence point is where we've added just as much base as we had acid, so that our pH is exactly at it is exactly neutral, okay? We can't really detect that very well, and we can do it with some means that we're not going to talk about in this class. There are some ways that we can do that so that we don't need to use an endpoint. And what the hell is an endpoint? Well, before we had nice ways to measure pH and things of that nature, we had to do this via endpoint detection. So an endpoint is where we can see that the reaction is finished. It's always past the equivalence point, and it's usually detected using something called an indicator. An indicator have different colors in their acid and base forms. So once the reaction between the standard and the NaOH is complete, then we start reacting with this indicator and the color changes. Okay? So the color of the solution changes. That we can see visually, and we know the reaction is completed. So the equivalence point and the endpoint are not the same volume of base. One is slightly beyond the other, and we try to get that as close together as we can, but one is beyond the other. The difference between those 2 points is called the titration error. So once the standardization is complete, then the standard can be used to titrate against an unknown. So we take our NaOH, we standardize it. That standardized solution can then be used to determine what the concentration of any other acid is, as long as we use it fairly quickly. And typical rule of thumb is within half a day of preparation. Okay, so as long as we've standardized it within a half a day, and then do the next titration at the same time, then we know what's going on. Okay, titration is always done more than one time to get the average of the values for the titration. Why? Because we tend to miss the endpoint the first time. It's just a fact of life. We tend to miss that first endpoint, and so we have to do this multiple times to make sure that we get a good value for that. All right, it's typically done at least 3 times. Okay. Indicators. Woo, we talked about indicators. Common pH indicators and their color changes. So we have phenolphthalein. It goes from colorless to pink. Bromothymol blue goes from yellow to blue. Methyl red goes from red to yellow. Bromocresol green goes from green to blue. Methyl orange goes from red to orangish. And crystal violet goes from green to blue. These all happen in different ranges, and that's what we were talking about. We want something that's going to be very close to where we expect our endpoint to be for this particular thing. All right. Now, these color changes are gradual, so ideally the endpoint would be detected as soon as the color goes from its acidic form to its basic form. Notice that there's always like a midpoint where we're halfway between them. That's what we're looking for in terms of endpoint. All right. So that's where we're typically trying to get to when we do this in the lab, if we're actually using a visual indicator. Okay. We call it the finally staying color. Persistent. Yes. All right. Oh my Lord, what the hell is this? Well, remember we put this up before, and we talked about the fact that we can, from a mass, that we start with, use the molecular weight to get to the number of moles. From the ballast equation, we know the relationship between the number of moles of our starting material and the number of moles of either our product or another starting material. And then we can go from those moles to mass. We can also do that with concentration. So if we know what the number of moles in a particular volume is, then we can go from concentration to number of moles by multiplying by the volume. We can then go from moles of one to moles of the second, and then from moles of the second to concentration, or moles of the second to a mass, or moles of the second to a volume, which we haven't talked about the volume part yet, but that's how we do this. Okay, so there are multiple ways that we can handle these kinds of calculations. This is what we're talking about for this, okay? Now, volume times molarity equals moles, so that's how we get this thing right here, all right? Questions, comments, problems on that part of it? So, as I've said before, when in doubt, convert to moles. When you have a mass, use the molecular weight to get to moles. When you have a concentration, you use the volume to get to moles. And from there, we can do a lot of the other things that we're talking about, okay? Example calculations. All right, we've got 2 of these. 25 milliliters of a 0.50 molar NaOH is titrated using until neutralized into a 50 milliliter sample of HCl. What is the concentration of HCl? Okay. So I have a volume of NaOH. Volume, concentration. So I can multiply those together to get the number of moles of NaOH. Once I know the number of moles of NaOH, then I can figure out the number of moles of HCl. Because it's a one-to-one relationship between the two of those in my balanced equation. So I can get to the number of moles of HCl. I can divide by the volume of HCl to get a concentration. So that's exactly what we're doing here. So this is our balanced equation. You always need a balanced equation to be able to do this. So I always do that first. So 25 mils of NaOH times the 0.50 moles per liter. Again, liter divided by 1,000 milliliters, because that cancels with the milliliters here. 1 mole of HCl per 1 mole of NaOH. 50 milliliters of HCl times 1,000 milliliters per liter. And again, we get the 1,000 here and the 1,000 here, so it's technically not required. And that means that we have 0.25 moles per liter. Well, that's interesting. I had 25 milliliters of 0.5 molar and 50 milliliters of 0.25 molar. Oh, there's a relationship there. Huh. Yeah, there is, and it's because it's 1-to-1. So since I have 25 mils of this, and it's at this concentration, if the volume that I have for this is twice as much, then I would expect that concentration to be half as much. Okay, that would make sense to me. So going through all the calculations makes sense. Is it always this pretty? Not always, but you know, it's easy to do with mathematics as opposed to in the lab. So it takes 83 milliliters of a 0.45 molar NaOH solution to neutralize 235 milliliters of an HCl solution. What is the concentration of the solution? Same equation. We're still reacting NaOH with HCl. I have 83 milliliters of the 0.45 molar NaOH, so I can multiply those two together to get moles of NaOH. From the moles of NaOH, I know the moles of HCl. I divide by the volume of the HCl to get the concentration in molarity. 83 mils of NaOH times 0.45 moles of NaOH per liter. 1 liter is 1,000 milliliters. 1 mole of HCl per mole of NaOH divided by the 235 milliliters of HCl. Again, converting that to liters, and I get 0.16 moles per liter. All right? Hopefully that makes sense to you. So remember, we are taking our volume times our concentration to get us to moles. For moles of this, I go to moles of this, and then I divide by the volume to get a molarity. All right? Questions, comments, problems on that? Awesomeness. That is the end of the material for that. Now, is it really that simple? Yes, actually it is. We do 8 million different calculations with that. Remember that I told you there were going to be a lot of calculations for the second exam, and we're going to have things all over this molar map, as we like to call it. So going from mass to moles, concentration to moles, we'll get to the volume to moles, from moles one to moles of another, then to mass, then to concentration, then to volume. And of course, we can always go to particles as well. So don't forget that all of those things are the case, all right? In order to be able to do that, we need to know things like the molecular weight, so the molar mass to be able to get from mass to moles, or concentration to get from, or the volume to get from concentration to moles. But those are the things that we're talking about for those. Questions, comments, problems? I hope not, but I know that it's going to take a lot of practice for you guys to get to that. So if you have any questions, let me know. Otherwise, I'm going to end this particular lecture, get this loaded for you guys, and then move on to the new material. All right. I'll talk to you next time. Thanks, guys. Bye.